Good afternoon, everybody, and thank you for coming to listen to this talk. Today, I will be talking about smart concrete. Yes, smart concrete. I know it's a rare definition, but concrete as another technology is not different. We have to adapt to the needs of the 21st century. As example, phones. Phone came from nowhere as a smartphone and changed our life. Concrete had to go through a transformation which can help us to reach the goal in this new century and face the new challenges and we see every day. Today, I'm talking about smart concrete like thermoelectric cement-based material as a cost-effective solution for harvesting energy. My name is Carlos Espinal, and I am a PhD candidate from Deakin University. This is an overview of what I'm talking about today. I will be talking about new generation of concrete, the thermoelectric effect, and how that fits into new generation of concrete, and how it can help to build a greener industry. I will be showing results on mathematical modeling and thermoelectric concrete and the implication of those results. But why we want to reduce the CO2 from the construction sector? Well, we have the targets to reduce the CO2 by 2050. And construction sector is one of the most polluting in the world. We have been working on mature and emerging technology. In mature technology, we're using low embodied carbon cement, capture, carbon capture technology, better design of the building, but the the life cycle of the concrete doesn't finish when we pour the concrete. We have to still the building. And through the serving life of the building, we need energy for lighting, cooling, and heating. And that consumption produces CO2. If we want to reach the goal by 2050, we have to help to reduce the consumption of the energy, consequently the producing CO2 from the serving life of the building. To do this, we had to think out the box. We had to innovate in different. And here is when the smart concrete come in. Smart concrete is a concrete that not only have good mechanical properties or good durability, but also have a special feature like sensing, melting snow, energy harvesting. As a sample, we have sensing properties that can work structural health monitoring that can help us to monitor the stress, temperature, microcrack, and moisture content of the concrete. That can help us to take care of the building better, reduce the use of the concrete in long term, and reduce the CO2. I've been working on energy harvesting. Concrete is exposed to different natural energies, light, mechanic, and heat. My studies focus on harvest energy from heat. But how I can do this? Well, I do this through the thermoelectric effect. Thermoelectric effect is produce usable electricity through a temperature gradient between two surfaces. And we evaluate, measure the thermoelectric effect through the Seebeck coefficient. The Seebeck coefficient can be calculated by measure the voltage between the temperature gradient between both surfaces. The Seebeck coefficient can be negative or can be positive. If negative, it means that electrons are the main dominator of the mechanisms and is known as an N-type material. If it is positive, holes are the main dominators and is known as a P-type material. But how feasible is do this in concrete? Well, we had to use additive to provide thermoelectric effect in concrete. Concrete have a negligent Seebeck coefficient, so we had to add special additives like carbon nanotubes or carbon fibers. Adding those type of materials into concrete is not new. We have been doing it for a while already to improve mechanical and durability of the concrete. But those materials also provide a new pathway for concrete, new technology, in this case, energy harvesting. As you can see here, many different fillers have been used, from the steel fiber, carbon-based material, and oxide. Different dosage in order to enhance the Seebeck coefficient. We have to keep an eye on electrical resistivity because it plays an important role when it comes to energy harvesting. But I'm gonna get back to this later on. So add a special additive to the concrete is not new. But not only that, also the concrete is widely used anywhere. If you walk right now, you're gonna see concrete. There is no city or a town in this world that doesn't have concrete. And these all structures are exposed to heat. The walls, the parking lots, the tubes, everything. So we're looking for exploiting this temperature regime and convert it into usable electricity. This is an example how it can be used. This is a photo taken in Victoria Parade, Melbourne. This road is all concrete, but not only look at the road, the walls, and the poles. We can estimate the energy output through this mathematical model, which depends on the Seebeck coefficient, has a square effect, and electrical resistivity. So, as I said earlier, we have to keep an eye on the electrical resistivity. The lower, the better, and the higher the Seebeck coefficient, the better. But it's not that easy. The perfect scenario is that we increase the Seebeck coefficient and reduce the electrical resistivity. Those two have a coupling effect. As I improve one, I get worse the other one. Get the perfect balance and how to enhance both of them for our purpose make part of the study, and many people have been researching that lately. Also, we considered the surface which the area surface is going to be exposed to the heat. In this case, we're assuming an area that is going to vary from 0 to 10,000 meters square, while the thickness is going to be 0.08 meters, and it's quite standard here in Australia, at least in Victoria. And an important thing to point out here is the efficiency factor. We're assuming a very conservative value because it hasn't been studied that much. So there is not much information in how this factor vary or behave. So we assume a conservative value in this case. The temperature regime that we're using to evaluate the energy harvesting are two. The first one is a constant temperature gradient from 0 to 20 and through 0 to 24 hours. This is most likely to be found in lab setups, but in real life, we don't have these temperature gradients. We have this one, which vary through the time. So we have a minimum and maximum value. Based on all these variables together, we created 4 scenarios. The first one, conservative. Constant temperature gradient, low Seebeck coefficient, and high electrical resistivity. The second one, we want to evaluate the impact of the Seebeck coefficient and electrical resistivity. So we use the same temperature regime than the first one, but increase the Seebeck coefficient and reduce the electrical resistivity. The third scenario, we actually want to see the impact of the temperature. So we keep the Seebeck coefficient electrical resistivity, but change the temperature regime to the second one, which is variable. And the fourth one is a much more realistic scenario, which we have a temperature can vary with the time, along with the Seebeck coefficient and electrical resistivity, which do as well, in function of the time, temperature. This is the first results. Scenario 1, conservative properties. And x-axis we have the time exposed, and the y-axis we have the exposure surface from 0 to 10,000 meters square and from 0 to 24 hours. And the contour graph means the energy output. If we assume 5,000 meters square in 12 hours, we harvesting around 6.5 kilojoules or over 12 in one day. It doesn't look like there's a huge amount of energy, but remember, it's passive and environmentally friendly. When we improve the Seebeck coefficient under the same conditions, we can increase from 6.5 to 155 kilojoule over 12 hours and around 300 in a day. This is a fair amount of energy, and it shows how important is keep researching ways to improve the Seebeck coefficient of cementitious materials. But these temperature gradients are unrealistic. We don't have those in real life. We have a variable temperature. So when we consider that, our energy output is reduced nearly by half, 60 kilojoule. But again, these are passive and environmentally source of energy, and it can help to complement alternative energies like solar energies, for instance. But what happens if we actually further enhance the Seebeck coefficient and reduce the electrical resistivity on a real temperature regime? We can increase the energy output from 60 to 150 kilojoule in 12 hours, or 800 kilojoule in 24 hours, and a 5,000 meters square. It would mean offset of 3 kilograms per day over 1 tons per year. If we increase the area that is going to be exposed to the sun, we're going to increase the energy output and reduce further this one. But most importantly, if we look at the efficiency factor, if we increase it from 0.1 to 0.2, 0.3, these 3 kilograms can become in 6, 7, 9 kilograms per day, 3, 4 tons per year, even 5, 5.5, just increasing a little bit. So imagine if we just increase at 1% or 2%. That would cause a huge impact in CO2 offsetting. This amount of energy in this condition are enough to charge batteries or user and sensor for structural health monitoring, help us to supplement lighting or heating, and can complement other technologies like solar energy or wind energy. In conclusion, I try to be as simple as possible, but this topic it is not as simple as it seems. It's complex and it needs further research. However, the results show potentials. This energy can supplement a source that is environmentally friendly and it doesn't produce CO2 as a subproduct. It can produce energy even in low temperature gradients. And as we scale up the concrete, we can harvest even more electricity. This technology can help us to reach the goal of net zero by 2050 and partially offsetting carbon emission. But really important, this concrete and this type of concrete can be the stepping stone for next generation smart concrete with energy harvesting capability. Imagine a building with walls and floor or parking lots that can produce electricity, along with solar energy or wind energy. That would be the building of the future. Thank you very much for listening, and hope everybody have a great afternoon. This is the reference. Thank you very much.